Welcome everyone. In this video, I will be covering section 14.7, maximum and minimum values. This section is dependent on chapter 4, Calculus 1 material. So I have posted the handout for theorems and key concepts for chapter 4. If you have a printout of that and you have it handy, then it will be helpful to follow the material for multivariables. What do the following statements mean? F has a local maximum at the point A, comma B. F has a local maximum at A, comma B if f of x, comma y is less than or equal to f at AB when xy is near AB. So that is local. So it has to be near the point AB. And f has an absolute maximum at AB. F has an absolute maximum at AB if f of xy is less than or equal to f of AB for all points xy in the domain of F. F has a local minimum at AB if f of xy is more than or equal to f of AB when xy is near AB. So anytime you talk about local, you will be using the word near, in the neighborhood of AB. F has an absolute minimum at AB if f of xy is more than or equal to f of AB for all points xy in the domain of F. In the domain of F. F has a saddle point at AB if f of AB is a local maximum in one direction and local minimum in another. In one direction, but a local minimum in another. So imagine a saddle. The saddle will have, if you look at it in one direction, it will be the highest point. It will be in the other direction. If you look at it, then um, it will be a maximum point. Then that is called a saddle point. Next, if f has a local maximum at AB, what can you say about their partial derivatives? It's kind of similar to the idea of calculus 1 material. Whenever you have a local maximum at a point, then there will be a horizontal slope there. So if the maximum is reached at C, then the derivative at C equal to 0. This is calc 1 when there is single variable. Here, there's only one derivative. So here with this function of two variables, so we have to talk about partial derivative with respect to x being 0 and partial derivative with respect to y being 0. So f has a local maximum at AB and the first order partial derivatives of f exist there, then partial derivative with respect to x at AB equal to 0 and partial derivative with respect to y at AB equal to 0. What is a critical point of F? So if I recap the idea of the same critical point that you did in Calculus 1 material, so you may want to pull up this handout that I posted for chapter 4, and I have posted again for this chapter. You notice here, it has all the information about chapter 4, which is the comprehensive graph, how you graph a comprehensive graph of a function using several information, like finding the domain, range, and then vertical asymptote, horizontal asymptote, and where the graph is increasing, where the graph is decreasing, and then where is it concave up, concave down, inflection points, then applying the first derivative test, second derivative test, and so on. So you have done all of this in chapter 4. So in chapter 4, we also talked about the critical number of a function f. Critical number of a function f is a number c in the domain of f such that the derivative is zero or it does not exist. That's a critical number. So the same idea is what we are going to extend here. There it was only one derivative. Now keep in mind we have partial derivative with respect to x and partial derivative with respect to y. A critical point of f is a point AB such that the first partial derivative with respect to x at AB equal to 0 and partial derivative with respect to y at AB is also equal to 0, or one of these partial derivatives does not exist. State the second derivative test. State the second derivative test. This is also known as the D test. Second derivative test or the D test. Suppose the second partial derivatives of f are continuous on a disk with center AB, and suppose that a partial derivative with respect to x at AB equal to 0 and partial derivative with respect to y equal to 0, precisely we are saying that these two conditions are satisfied. That means the point is a critical point. That is, AB is a critical point of F. Let D be represented as D of AB, which is equal to the representation F x x, partial derivative of F with respect to second order partial derivative, F x x AB, second derivative with respect to x, the second partial derivative with respect to y at AB minus the mixed partial derivative fx at second mixed partial derivative fxy at AB, the whole square. If this representation is, this expression on the right hand side is represented as D, let's take various cases for D. If D is positive, along with the second partial derivative with respect to x is positive also, then f of AB is a local minimum. If D is positive and second derivative with respect to x, second partial derivative with respect to x at AB is less than 0, then f of AB is a local maximum. If D is less than 0, then f of AB is not a local maximum or minimum. The point AB is a saddle point. So you notice here, for D more than 0, you have two conditions, but for less than 0, there is only one. So D more than 0 along with second partial derivative with respect to x is positive also. then f of AB is local minimum. So if you look at this particular condition, and if you compare the result that you did in Calculus 1, Chapter 4, so it is a second derivative being positive. So it is kind of concave up condition. So this is from Calculus 1. So if you look at this second derivative test, the f double prime is continuous near C, and f prime C equal to 0, and if f double prime C is positive, then there is a local minimum. So it's kind of concave up, therefore there is a local minimum. So it is f prime C equal to 0 and f double prime C less than 0. It is concave downward, this is concave upward, then there is a local maximum. So for concave up, there is a valley, that is concave down, there is a peak. So it's a local maximum. Here valley, local minimum. This is the case when you have f double prime positive. Here f double prime negative. Kind of similar idea that we see here also, along with the condition D positive. So if the second partial derivative with respect to x positive, there is a local minimum. If second partial derivative with respect to x negative, there is a local maximum. One way of connecting the information that you already learned in Calculus 1. So based on this information for finding maximum and minimum, applying the d-test or second derivative test, d-test or also known as second derivative test, the problem number 10 is exactly based on that information. So please refer to the videos for section 14.7 for this problem number 10. Now let's take the extreme value theorem for functions of two variables, which is finding absolute maximum and absolute minimum. If f is continuous on a closed interval, what is a closed set in R2? What is a bounded set in R2? In order to do extreme value theorem, we need those definitions. A closed set in R2 is one that contains all its boundary points. A closed set is considered to be one which contains all its boundary points. If one or more points on the boundary curve are omitted, then the set is not closed. A bounded set is one that is contained within some disk. In other words, it is finite in extent. So we've understood what we mean by closed set and a bounded set. Then extreme value theorem for functions of two variables. If f is continuous on a closed and bounded set D in R2, then f attains an absolute maximum value f of x1, y1, and an absolute minimum value f of x2, y2 at some points x1 and x1, y1 and x2, y2. The restriction here is that f is continuous on a closed and bounded set D in R2. If you have that condition, then there will be extreme values, meaning there will be absolute maximum and an absolute minimum value at x1, y1, and x2, y2 at 2 points. Again, extreme value theorem is only an extension of the extreme value theorem that you did in Calculus 1 class for single variables. So if you look at that one here, extreme value theorem, if f is continuous on a closed interval, so that closed interval gets translated to closed bounded set D and R2 when you do two dimension, when you do function of two variables. F attains an absolute maximum value, f of c, and an absolute minimum value at f of d at some numbers c and d in the closed interval ab. So here, if f is continuous in a closed interval ab, we are guaranteed that f has an absolute maximum and an absolute minimum inside of that interval ab. The similar idea here, only thing is it should be um, continuous on a closed and bounded set. How do you find the values at the extreme value theorem guarantees? How do you find those extreme values, those absolute maximum and an absolute minimum that the extreme value theorem guarantees? Find the values of f at the critical points of f in D. Step number one. That is step one. Step two, find the extreme values of f on the boundary of D. Extreme values of f on the boundary of D. Then the third step, the largest of the values from the above steps, from step number one and step number two, is the absolute maximum value and the smallest of these values is the absolute minimum value. So we have to follow these steps. So in order to find out the extreme values that the extreme value theorem guarantees, first of all, we notice that extreme values will occur only when the function f is continuous on a closed and bounded set D. Then we have to first find out the critical points. If you recap what critical points are, we mentioned what critical points are earlier. What are critical points? Critical points are those at which the partial derivative with respect to x equal to 0 and partial derivative with respect to y at AB equal to 0. Those are critical points. So first we have to find out the critical points and then find the values of f at the critical point. So if let's say you have found out a1, b1 and a2, b2 are two critical points, then you have to find out f at a1, b1 and f at a2, b2. Those are the values of f at those critical points. Then find the extreme values of f on the boundary of D. This part may be the challenging one in problems. So we have to find out the boundary, and then if let's say the boundary is like a square, then you have to find out um, at every side of the square what the extreme values of f are. What is the maximum? What is the minimum for on the boundary? Then the largest of the values. So let's say you get extreme values on the boundary, and also you have found out values of f at the critical points. So in these two steps, you have several values. The largest of these values from these two steps is the absolute maximum value. The smallest of the values in step one and step two would be the absolute minimum value. Again, the idea that just you saw is exactly similar to the closed interval method to find the absolute maximum and minimum values of a continuous function f on a closed interval ab. Find the values of f at the critical numbers of f, this is single variable, in the open interval ab. In the open interval AB, here it is AB is an interval. Find the values of f at the endpoints of the interval, which is kind of boundary. Boundary. The word is equivalent for the endpoints of the interval is boundary of the domain. Boundary of the domain D in function of two variables that we saw. The largest of the values from step 1 and step 2 is the absolute maximum value. The smallest of these values is the absolute minimum value. Kind of you can relate what you studied in calculus 1 single variable, same technique, then we are extending that to multivariables. So based on this theorem, extreme value theorem, to find out absolute maximum and absolute minimum, we have, you see some problems here, number 33, and also a word problem, number 53, and also there is another problem here, number 41. You might have seen these kinds of problems in Calculus 1 material as well, but we are going to do by the techniques that you have learned in Calculus 3 class now. And these problems are done in the videos for section 14.7. Please refer to those videos for further practice. Problem number 33, 53, and 41, and earlier one other problem number 10. All these are done in the videos, please. And also number 5. Number 5 is also done. Number 5. Yes, this problem. Number 5 is also done in the videos. Please take a look at them. Then I will, please join me for the next video on 14.8.